After studying the simple pendulum, you might be concerned with the fact that a real physical pendulum has a string with mass, and the distribution of mass is not that of a point bob. Let's go one step forward and study something closer to reality. Consider a potato-shaped object. Assume that it is hanging from a point in the ceiling, and assume you displace it a little bit from its equilibrium position. There you have a physical pendulum. Although this works for any shape of object, this does not need to be a potato though. Any physical pendulum is an object that oscillates like a pendulum but cannot be described by a point bob and a massless string. When a pendulum is hanging and it oscillates, it does so because of the torque acting on it. Remember that where there is a torque, there is a change in angular momentum, and therefore a change in omega, the angular velocity. The torque in this case is due to the force of gravity acting on the center of mass of the potato, also known as pendulum. The torque is the cross product of the position times the force. The position vector goes from the fulcrum to the point where the force is acting. This is the center of mass of the pendulum. The force of gravity points straight down. The torque is equal to the moment of inertia times the angular acceleration alpha. Here, the torque is going to depend on time, as the force of gravity needs to be projected in the direction perpendicular to r, and the angle changes as the pendulum oscillates. We can write the equation of the torque explicitly and work a bit on it. For that, I will call L to the distance from the fulcrum to the center of mass of the pendulum. The angular acceleration is d2 theta over dt2. Look that when the angle is positive, the acceleration is negative. When the angle is negative, the acceleration is positive. This is, the acceleration points opposite to the angle. The force points against the angle. This equation is the second derivative of the angle equal to a negative constant times the angle. Again, the differential equation for the simple harmonic oscillator. Here theta naught is the maximum angle, the amplitude, and omega is the angular frequency. The angular frequency, given by the square root of mgl over moment of inertia. Analogously, for the period of the oscillations, you can use a pendulum or any object that follows simple harmonic oscillations, such as an elastic spring, to characterize an earthquake, for example. You can set the spring or the pendulum to be sensible to the vibration from an earthquake. The amplitude and frequency of the oscillations can tell you a lot about the earthquake. May science be with you.